Welcome everyone. So we're going to officially talk about sequences and go over more examples on the method of induction. Well, so how do we define a sequence? What is a sequence? And what is the connection between a sequence and a series? Well, remember that we define a sequence as a function. So, definition. A sequence which is usually denoted by A sub n, or f of n is a function with domain. This domain is usually n, natural numbers. Sometimes we use whole numbers as the domain. So a sequence A sub n equals to f of n is a function with domain equals to n natural numbers and sometimes they use whole numbers. Sometimes they say, hey, let us use A sub 0, or the domain is W, the whole numbers. So how do we define this function? This function actually takes on values from n or W, domain n or W, and maps them to the codomain R, real numbers. It takes on numbers like n and maps those numbers into A sub n or terms of the sequence. So this function takes numbers like n and map them into real numbers A sub n, real numbers A sub n. Okay, sometimes we denote a sequence this way. We say that, hey, sequence A sub n is equal to the set of all elements in the range, like A sub 1, comma, A sub 2, comma, A sub 3, comma, the rest of the terms. They put A sub n as general term inside curly brackets. So this guy is called the general term. General term. A sub 1 is the first term of the sequence. First term. A sub 2 is the second term. Second term. A sub 3 is the third term, and we continue this process. So now that we define a sequence, we can take the terms of the sequence, add them together to define a series from sequence to the series. We take the terms of a sequence add them together, and we call it series. Add them together, and we call it series. Well, in calculus, you saw that we use summation notation, which is ugly S. The summation notation is Greek letter sigma or ugly S. So this is sigma. For example, think about it this way. We take A sub 1 plus A sub 2 plus A sub 3 plus ... plus the last term, A sub m, and we denote it by the summation notation, sigma A sub n, A sub n. N starts from 1 and it stops at m. We call this a series. Here you have expanded form, and here you have summation notation for your series. On the right-hand side, you write it in nice compact form using summation notation, and on the left-hand side, you have the expanded form. For example, suppose A sub 1 or the first term of your sequence is equal to -2. The second term of your sequence is equal to -1. Then the third term is equal to 0. The fourth term is 1. And the fifth term is equal to 2. Question says, hey, compute the following series. What is the sum of A sub k's such that k starts from 1 and stop at 5? B says, after you calculated the first series, now calculate this series for me. The sum A sub 2k. So I'm changing the index into 2 times k. But my k starts from 1 and it stops at 2. So for part A, it says, hey, you have A sub k and k starts from 1. So you plug in 1 for k and you get A sub 1. So my very first term is A sub 1 plus, look at the definition. Then I plug in 2, I get A sub 2 plus, I plug in 3, A sub 3, then I plug in 4, A sub 4, then I plug in 5, A sub 5. So what is A sub 1? minus 2. A sub 2 minus 1. A sub 3, 0. A sub 4, okay, is 1. And A sub 5 is 2. By adding all of these together, you see the result is equal to 0. Perfect. Okay, so you have 2 times k. Whatever your k is, your result is A sub 2 times that k. So my first k is 1. So 1 times 2 is 2. So I'm adding A sub 2 plus my second k is 2. 2 times 2 is 4. So my second term is A sub 4. What is A sub 2? Negative 1. What is A sub 4? 1. So if I add these together, the result is equal to 0. Very well. So now that we talked about summation notation, sigma, let us get back to the example that we did last time, and we used induction. Last time, we introduced induction, and we said that in the process of using induction, we have a statement. A statement denoted by P of n. And our goal is to prove that statement. So we call that in mathematical induction, we have a statement. That statement is denoted by P of n. This n belongs to a domain. That domain might start from 1. In any question that we see about induction, they specify that that n starts from what number? It might start from 2. They mentioned that. It might start from 3. Sometimes it might take some values like 0. But in any question related to induction, they definitely mention that 1 is the smallest value in the domain. So to apply induction, we say that, well, they have a very base step. We say that, suppose Pn is a statement that satisfies the base step. What is the base step? The base step is the very first step that you take the smallest value in your domain and you show that P is true for that smallest value in the domain. More space. So we have a statement Pn in the base step. We show that it is true. P is true. For the smallest value in the domain. After we show the base step, we go to inductive step. In inductive step, we say that, okay, now suppose this statement, P is true for any number less than or equal to n. Suppose that P is true for any value like k, which is less than equals to n. We assume it is true. We have to have something to work with. We show that this is your job, that P is true for the next number, which is k plus 1. If this is true, then you say that, hey, by mathematical induction, this statement is true for any number in that domain. So if p of k plus 1 is true, then p is true for any n. Okay, this is what we learned before. And we went over one example. It says, this is an example. This will recall for you. Show that 1 plus 2 plus 3 plus n, the sum of first n natural numbers is n times n plus 1 divided by 2. Okay, so we have a sum of some numbers. I expect you to ask, you just talked about summation, the ugly S or sigma. Can I use that here? So another way to write this sum down is sum sigma k such that k starts from 1 and stops at n is equal to this formula on the right hand side, n times n plus 1 divided by 2. So we took 1 plus 2 plus 3, the sum of first n natural numbers, and we use the summation notation, series notation, to represent this sum. Instead of keep writing these numbers, we can use this beautiful, nice, compact formula representing the sum of the first natural numbers. Okay, perfect. So, example. Suppose the question says, well, what is the sum of 2 plus 4 plus 6 plus plus 500? What is this sum? Using the formula here. The second one says, well, what is the sum of 5 plus 6 plus 7 plus 50? How do we use the formula here that we just represented to calculate these sums? Well, to solve the first one, look at the formula. The formula starts from 1. Then you have 2. It means that you have a bunch of even odd numbers, and the sum is n times n plus 1 divided by 2. But this set starts from 2. Then it goes to 4. Then 6, and so on. How can I translate this guy into this form? Okay, what I'm going to do, I'm going to factor out 2 from all of these. I'm going to say, hey, let me factor out 2. If I factor out 2, this guy is now 1. Then I have 2. Then I have 3. Then I have 4, 5, 6, 7. And if I factor out 2 here, I get 250. So what I'm trying to calculate, I'm trying to calculate 2 times the sum of first 250 natural numbers. So I'm going to copy down 2. So it's going to be 2 times. This follows the formula n times n plus 1. What is n? N is 250. 250 times 251 divided by 2. I can cancel out these 2. After doing the multiplication, the number that I have is going to be 62,750. Perfect. So what do we have here? We have 5, 6, 7, 50. It doesn't start from 1. So 1, 2, 3, and 4 are missing. Okay, 1 plus 2, 3, 3, 3, 6, 10. So 10 is missing from this sum. So what I'm going to do, I'm going to use the formula n times n plus 1 divided by 2 and then subtract 10 out of it. So this can be written as 50 times 51 divided by 2 minus the first sum, which is 10. It doesn't have 1, 2, 3, 4 that I can use to follow the formula. Instead, I'm going to follow the formula and subtract 1 that I added here. So if you do the calculation, the sum is equal to.
Professor, I actually have a question.
Yeah, of course, go ahead.
Okay, so why minus 10 though?
So take a look at this. Let's rewrite this back for you. So what I'm going to do, I'm going to add 1, 2, 3, 4 to this number set here. So I'm going to add 5, 6, 7 plus 50. So I can use the formula up here. 50 times 51 divided by 2. But since this is just a statement, this is a sum, I cannot just add a number. To balance it, I have to subtract it as well. So I'm going to at the same time subtract 10. This is 4 plus 3 plus 2 plus 1, which is 10. So I'm adding and subtracting 10 because I want to use the formula.
Oh, okay. I see what you're doing is that you're subtracting the numbers that are not there.
Very good. Excellent.
Okay.
Excellent. So this
Let's just say it is like 10 plus 11 plus 12. You add the numbers from 1 to 9 and then minus that with the sum of, okay.
Perfect. 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 12, 65. Well, now we're going to use mathematical induction to prove what you learned in calculus. Very well. We're on 5.2. Example. Through the geometric sequence sum. Which is r to the power 0 plus r to the first power plus r to the second power plus dot 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 r to the n power equals to r to n plus 1 minus 1 divided by r minus 1, and r is not equal to 1. This is what we learned in calculus. But how do we prove it? Well, prove by contradiction, prove by contraposition, direct definition, induction. Well, we just learned some new techniques. Let us use them. Prove by mathematical induction. So remember that in mathematical induction, you have a statement. This statement, let us denote this by P of n. This is our statement, which says r to power 0 plus r to the first power plus r to the second power plus dot, 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 r to the n power, if you add all of these together, closed form, this is equal to r to the n plus 1 minus 1 divided by r minus 1. We have this condition that r cannot be equal to 1. So in mathematical induction, we say that we have to prove the base step. The base step says we need to show that this statement is true for the smallest value in the domain. The smallest value in the domain is 0. The smallest value in the domain is 0. So I need to show P of 0 is true. P of 0 is true. Let me put a question mark next to this because I'm trying to show that. P of 0, my left-hand side is r to the power 0. My right-hand side, I'm going to plug in 0 for n. What do I get? I get r to the power 1 minus 1 divided by r minus 1. Okay, this is r minus 1 divided by r minus 1, which is equal to 1. R to power 0 is also 1. So we just showed that left-hand side is 1, and it is equal to right-hand side, which is 1. So we're happy about our base step. Now let us move on to inductive step. Inductive step says, okay, now that we showed that the base step is true, suppose this formula is true for any k less than equals to n. We need to have something to work with. Suppose P is true for any k less than equals to n. What's the meaning of that? It means that r, r to the power 0 plus r to the first power plus r to the k power is equal to r to k plus 1 minus 1 divided by r minus 1. This is true. We have this formula. We have this equality. Now we need to show that. We need to show that P is true for k plus 1. What's the meaning of that? It means that if I plug in k plus 1 for n, left-hand side and right-hand side are equal to each other. Okay, let us begin. So it means that we need to show that r to the power 0 plus r to the first power plus dot, 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 r to power k plus r to power k plus 1 is equal to, so I'm going to put a question mark here, r raised to power k plus 1 minus 1 divided by r minus 1. This is what we're trying to prove here. So let me use a different color. So you see I'm trying to prove this for k plus 1. This is k plus 1. I'm changing k into k plus 1. It means that wherever I see k, I replace that with k plus 1. And I'm putting a question mark here because I have a left-hand side, I have a right-hand side. Okay, we're going to use what we have here. Let's put this one in the green color because we're going to use this substitute that here. So take a look at this sum here. This sum is r to power 0, r to power 1, r to power 2, r to power k, which we already know is equal to this fraction. This is r to power k plus 1 minus 1 divided by r minus 1. I'm going to write this term next to this guy and take the common denominator. Plus r to the power k plus 1. If I take the common denominator between these two, what I get, let me write down this guy on this side, so we have enough space, r minus 1, r to power k plus 1, minus 1 plus r to power k plus 1 times r minus r to power k plus 1. Okay, as you can see, we can cancel out these two terms. They are opposite of each other. So you're left with r to power k plus 1 times r, which is r to power k plus 2 minus 1 divided by r minus 1. So this guy is actually r to power k plus 2 minus 1 divided by r minus 1. These two are equal to each other. So we're done with the proof. Well, now I expect you to ask, okay, Professor, you keep using induction for equality, for equations. What if I have inequality? Can I use induction? And if yes, give us an example. I have one example for you. Induction for inequalities. Well, suppose I ask you to prove this. Suppose I ask you to show that for n greater than or equal to 0, 2 raised to 2n minus 1 is divisible by 3. So let's take a look at the application of induction in divisibility. Then we move on to another example related to inequalities. Okay, perfect. How do you show that 3 divides this expression here? Well, direct definition, counter example, okay, contradiction, contrapositive. Well, let us try induction. So induction says, hey, if the base step is true, then the rest is not that hard. Prove my induction. So base step. Let us try our base step. Base step says, well, just show that this statement, this is your P of n. This statement is for is true for the smallest value in your domain. So this is my base step. Show that it is true for n equal to 0. Okay, so if I plug in 0 here, it says 3 divides. 3 divides. 3 is a factor of 2 to power 0 minus 1, which is 0. It says 3 is a factor of 0. Or 0 is a multiple of 3. Is this true? Of course it's true. 0 can be written as 0 times 3. So my base step is true. What's the meaning of that? It means that I can move on to the next step, which is inductive step. Inductive step. Suppose this guy is true for any number like k less than or equal to n. Suppose 3 divides 2 to 2k minus 1 for all k values less than or equals to n. Suppose this is true, and I'm going to put this as a true statement in a green color. This is true. We have this as a true statement. We know this is true. We don't have any problem with that. What are we going to do? We're going to show that this is true for the next number, k plus 1. We need to show that three divides 2 to 2 power 2 times k plus 1, k plus 1 minus 1. So wherever I see k, I write down k plus 1. This is what I'm trying to prove. Let's put a question mark next to it. This is what we're trying to prove. Okay. One of the methods is to try to write this expression the way that 3 appears somewhere. So we are going to try to break 3 raised to 2 times 2k plus 1, I'm sorry, 2k plus 1 minus 1 down. So how do we do that? So this is 2. I'll keep writing 3. So what I'm going to do, I'm going to write this way. 2 raised to 2 times k plus 1 minus 1 is equal to, I'm going to distribute 2 into parentheses. I get 2 raised to 2k plus 2 minus 1. This guy, you're adding the exponents. So you can break this guy down into 2 raised to 2k times 2 to the power 2 minus 1. 2 to 2k plus 2 is now 2 to 2k times 2 to power 2. This is 4. 4 is 3 plus 1. So this is equal to 2 to 2k times 4 minus 1, which is equal to 2 to 2k, 3 plus 1 minus 1. Now I'm going to distribute 3 to 2k into parentheses. One more time. Base step is true. We don't have any problem with n equal to 0. Why is that? Because 3 divides 0. 3 is a factor of 0. 0 can be written as 0 times 3, which is always true. We're good with the base step. Inductive step. Inductive step says, suppose 3 divides 2 to 2k minus 1 for all k's less than equals to n. Again, we're going to put this in green because this is true and we're going to use this. This is true. Now, our job is to prove this for k plus 1, the next number, like a domino. You show that 3 divides 2 raised to 2k plus 1 minus 1. This is what we try to prove. One technique is to break this expression down into the terms that have 3 in them. So let us break 2 raised to 2k plus 1 minus 1 down. How do we do that? We're going to play with the exponents. 2 raised to 2k plus 1 is equal to. I distribute 2 into parentheses. Let us write down -1 as well. We don't want to lose that. 2 to 2k plus 2. I'm going to copy down this constant here. This is 2 to 2k plus 2. Recall that if you have 2 to power n plus m, this is 2 to the power n times 2 to the power m. So if you have the same base, you can just write one base and add the exponents or vice versa. So this can be written as 2 to 2k times 2 to the second power minus 1. Multiplication comes first. This 2 squared doesn't belong to minus 1. You cannot do the subtraction here. You have multiplication to deal with first. So this guy is 2 to 2k times 4 minus 1. 4 is 3 plus 1. So I'm going to use a different color so you see what I'm doing here. Okay, perfect. So I have 2 raised to 2k times 3 plus 1, which is my 4. 3 plus 1. And remember that you have a constant minus 1 here. So I'm going to distribute 2 to 2k into parentheses. Again, we're trying to break this guy down into terms with 3. So here you get 2 to 2k times 3. Well, I'm lucky. I'm having 3 next to this, plus 2 to 2k minus 1. Well, what do you see here? You have this term with 3 in it. What's the meaning of that? It means that 3 divides this expression here. So 3 is a factor. It's a factor here. Now look at 2 to 2k minus 1. I'm going to use what I have as my inductive step. It says, well, since you have 2 to 2k minus 1, I already know that by inductive step, 3 divides this expression. 3 is a factor. So 3 is a factor of this term. 3 is a factor of this term. 3 divides the whole expression on the right-hand side, which is equal to this expression on the left-hand side. So it says 3 divides this expression on this side, which is equivalent to 2 raised to 2k plus 1 minus 1. So 3 divides 2 to 2, k plus 1 minus 1. And we prove by induction.